লেজার। মানব সভ্যতাকে বদলে দিয়েছে যে কয়েকটি প্রযুক্তি, এটি তার মধ্যে অন্যতম। বিংশ শতাব্দীর দ্বিতীয়ার্ধে লেজারের আবিষ্কারের পর খুব অল্প সময়ের মধ্যেই এটি বিজ্ঞানের বিভিন্ন ক্ষেত্রে বিপ্লব ঘটাতে শুরু করে। চোখের ল্যাসিক সার্জারি থেকে ইলেকট্রনিক মাইক্রোচিপ তৈরির মতো গুরুত্বপূর্ণ কাজে উচ্চ ক্ষমতার বা হাই ইন্টেন্সিটি লেজার ব্যবহৃত হতে থাকে। 1970 ও 1980-র দশকে বিজ্ঞানীরা চেষ্টা করছিলেন কিভাবে আরও বেশি উজ্জ্বল লেজার রশ্মি তৈরি করা যায়। এই জন্য তারা বিভিন্ন ক্রিস্টাল পদার্থ নিয়ে গবেষণা করছিলেন। আসলে লেজারের মধ্যে এই ক্রিস্টাল পদার্থই অ্যাম্প্লিফায়ার হিসেবে কাজ করে আলোর ঔজ্জ্বল্য বাড়িয়ে তোলে। কিন্তু তাঁরা বেশি দূর এগোতে পারছিলেন না, কারণ আলোর ক্ষমতা এতটাই প্রবল হয়ে উঠেছিল যে সেই আলো ক্রিস্টাল পদার্থের মধ্যে দিয়ে যাওয়ার সময় তাকেই পুড়িয়ে ধ্বংস করে দিচ্ছিল। এই চ্যালেঞ্জ দূর না করতে পারলে আরও উচ্চ ক্ষমতার লেজার তৈরি অসম্ভব ছিল। এই সমস্যার সমাধানে মার্কিন যুক্তরাষ্ট্রের রচেস্টার বিশ্ববিদ্যালয়ে গবেষণা করছিলেন অধ্যাপক জেরার্ড মুরু ও তাঁর পিএইচডি ছাত্রী ডনা স্ট্রিকল্যান্ড। 1985 সালে তাঁরা প্রকাশ করেন এক যুগান্তকারী গবেষণাপত্র, যেখানে তাঁরা প্রথমবারের মতো তুলে ধরেন চার্পড পালস অ্যাম্প্লিফিকেশন বা সংক্ষেপে সিপিএ নামক এক অভিনব প্রযুক্তির কথা। এই পদ্ধতির মাধ্যমে লেজারের ক্ষণস্থায়ী আলো বা শর্ট লেজার পালসের ক্ষমতাকে অনেক গুণ বাড়িয়ে তোলা সম্ভব, এবং সেটা অ্যাম্প্লিফাইং মাধ্যমের ক্ষতি না করে। এই গবেষণা উচ্চ ক্ষমতার লেজার প্রযুক্তির ক্ষেত্রে এক যুগান্তকারী মাইল ফলক স্থাপন করেছিল। এই অসামান্য আবিষ্কারের স্বীকৃতি স্বরূপ ডনা স্ট্রিকল্যান্ড এবং জেরার্ড মুরু 2018 সালে পদার্থবিদ্যায় নোবেল পুরস্কারে ভূষিত হয়েছিলেন। নোবেল পুরস্কার পাবার পর থেকে ডনা স্ট্রিকল্যান্ড বিভিন্ন সাক্ষাৎকারে তাঁর গবেষণা ও জীবনের কথা তুলে ধরেছেন। আজ আমাদের তরফ থেকে তাঁর সাথে আলোচনায় বসেছেন তাঁরই সহকর্মী bigyan.org.in এর সহ-প্রতিষ্ঠাতা ডক্টর রাজিবুল ইসলাম। এখানে শুধু তাঁর বর্তমান গবেষণার কথাই নয়, বরং নতুন প্রজন্মের হাতে কলমে বিজ্ঞান শিক্ষার গুরুত্ব নিয়ে তাঁর ভাবনার কথাও উঠে এসেছে। অধ্যাপক স্ট্রিকল্যান্ড আমাদের ঘুরিয়ে দেখিয়েছেন তাঁর নিজের গবেষণাগার। এছাড়া তাঁরই পরিচালনায় স্নাতক স্তরের শিক্ষার্থীদের জন্য তৈরি আরেকটি গবেষণাগারও ঘুরে দেখেছি আমরা, যেখানে তিনি তরুণ ছাত্রছাত্রীদের আলোকবিদ্যার মজা দেওয়ার জন্য তৈরি করেছেন এক বিস্ময়কর পরীক্ষা, যাতে লাল আলো বদলে হয়ে যায় নীল আলো। bigyan.org.in এর ওয়েবসাইট, ইউটিউব চ্যানেল ও ফেসবুক পেজে রইল সেই মূল্যবান কথোপকথনের ভিডিও।
So tell us, what made you excited in the first place? Why did you want to do experiments?
That is an interesting question. Why did I want to do experiments? So I went as an undergrad to McMaster University because they had a program in lasers and electro-optics. And in the 1970s, you didn't see lasers. And so that just sounded really cool. And so I think as soon as I decided I want to do lasers, well, then you want to see the laser. You don't want to just think about it. You want to actually play with the laser. So that's why I got started, and I've always been with lasers ever since.
But growing up, were you a very hands-on person?
No.
Okay.
No, I'm not one that fixed a car. I'm not one that, I know I took, my parents had this very fancy clock beside their bed that looked like a crystal, but it wasn't. It was just glass. Anyways, I managed to take it apart, but I didn't get it back together. I think I got in a lot of trouble for that. So I could take it apart, but I couldn't put it together. But and maybe I didn't try again after that.
Mm-hmm. Yeah. And then when you were working in the lab, where at any point of time, did you think you want to do theory first, understand the systems theoretically first, and then do hands-on? No. So what's your approach when you have you have a bunch of equipment? Do you want
I just have an idea, and then I see if it works. It's not, and then hopefully somebody else will do the simulation more than me. I'll say how it should be done, but not do the actual thing myself, because I hate computers. And if you have to use a computer, then I don't want to do it. You can edit that out, but it's a fact. And so, yeah, it's more an idea, But certainly my grad students have to do the simulations now to see why it's not working the way I think.
Mm-hmm.
But it's a hard fight with me. If I think it should be some way, I really think it.
But as an experimentalist, we measure, right? We
That's
measure
right.
the universe as an experimentalist. And sometimes, at least in many countries, when we learn science for the first time, it's usually the other way, right? We learn the theory, and then we usually go to a lab.
But that's because it's easier to teach on a blackboard theory. It's very hard to teach experimental work standing at a blackboard.
Mm-hmm.
That's why.
That's why. But it should not be, it doesn't have to be that way.
No, and I would love to change it. That's why I am making these new labs, even to start in first year, so they can see the excitement of seeing something for the first time before anybody else gets to see it.
So can you tell us more about what are these labs and what's the philosophy behind it and some examples?
So the philosophy behind it is the fact that I think that in education, in science, we're always talking about what everybody has already learned, and science is all about what we don't know. And so it is so much fun to know you're the first one seeing something work, right? And so I want to get that excitement into the undergrads. And so the one we're going to do that's in my field is just something that came along when the laser came along. The laser was so intense, it could have 2 photons be absorbed at the same time and make 1 photon twice the energy. So we're going to have the students in first year, so they don't know the theory at all. We don't teach it to grad school, but they're just going to see it happen and hopefully wonder why. Hopefully be even amazed that an infrared beam of light turns into a blue beam of light, and wonder why. And then that's the point, is that can they come up with a little model?
And so
we'll lead them through it, but they're not to compare to a model. They're to come up with, from the experiment, see if they can figure out what the model is.
I see. So when they're doing these experiments, they don't necessarily know the underlying theory yet, right?
No, they're supposed to see if they can even, but we will of course be helping them along. We will be telling them, well, let's see how it changes if we change the energy of the laser pulse. Let's see if we change the pulse duration of the laser pulse. We will teach them that peak power is energy per unit time. So, and then also the point is that everybody's constrained. Theorists are constrained by how complicated a thing they can calculate, and they have to make approximations. Experimentalists are constrained in what we can measure. So they're only going to get to measure the energy of the blue, right? So they have to just take that one measurement when they change the peak power. When they change the focusing and so change the power per unit area, they're still going to measure the energy. And they have to still be able to go from there and walk back and just see from that kind of measurement, can we see all the way back? So it's a few things. It's like, can we make the understanding of it? How do the constraints of what we can do experimentally work, right? They'll also see that they can't actually measure the peak power of the laser pulses because our pulses are so short that you need the laser pulse itself to measure itself, right? Which we will do with them in the lab as well. But it's this idea is that we are constrained as experimentalists, but we can still figure things out. And how do we go about and do it? And so it's also to teach them what is it to be an experimentalist, right? Not only do you get the excitement of seeing something new, especially optical scientists, we don't just see blips on a screen or we don't just see some kind of data, we actually see the light changing before us. If money was not an object, I would have done white light generation. I would have gone in and shown that through nonlinear optics you could make every color of the rainbow, because to me that's one of the really beautiful things we get to see, right? But anyway, we're going to stick with what we're doing. But I think it's a few things, the excitement of it, but also just to understand what it means to do an experiment. You have a certain set of data, that's all you've got, and what can you derive from that?
Fundamentally, if we look at the history of science, or even how science is done now, we do measurements, and as time progresses, we do more and more precise measurement, right? And then we learn a lot about nature. So in these experiments that you are designing for the undergraduate students that you are describing, are those experiments more qualitative, or are you also teaching them about measuring things more precisely?
This one will be more probably qualitative because it's really, we're just going to change things by a factor of 2. We'll change the energy by a factor of 2 and see how much does the frequency doubling change. You know, whether it's the pulse duration by a factor of 2, the beam area by a factor of 2, the energy by a factor of 2, what happens? And so it'll be pretty rough. On the other hand, from not pretty rough, you can tell if it's going in a nonlinear way or a linear way. And then there's 3 inside intensity, the peak power and the energy's inside. And so how do you parse out which is which? But it's not a precise measurement. That's a different type of experimental work.
So these experiments that you are mentioning, this is, of course, very exciting to us, people working with optics. But this requires certain kind of equipment.
Yes.
So in general, if you talk about, let's say, school kids, high school kids, or beginning college, when people are learning science, they don't necessarily have the same kind of equipment. So how would they, in your opinion, how would they still create this excitement about measuring?
But years ago, there was a scientist, Steve Jacobs, at the laser lab, and he came up with this optics suitcase. And schools could afford them. They weren't that expensive. And it came with a whole kit of things that you could either do to make jello optics, or you could do the cross polarizers and watch how the light came through, and the light didn't come through, because that's even just a remarkable thing itself, to try to understand the wave nature and the fact that it may oscillate in one direction and not the other direction, and what happens.
You can use sunglasses to do that.
And you can use your own sunglasses to do that. So, you can also just set up different optics to see it. You can actually start even, seeing how, although it wouldn't be right for high school, maybe, but the Fourier transforms. I mean, this is also something that optics is a beautiful thing that actually shows you math out there right in front of you, right? And so there's some cool experiments you can do that by, putting something through a grid pattern and then getting rid of the grid pattern and showing the picture back up again, all through spatial filtering. So there's things you can do that are just cool, and think, how does that work?
Okay, so that is super exciting. Shall we go and see your labs now? You said you want to show us both your undergraduate teaching lab and also your research lab.
Okay.
Yeah.
So this is the laser that we're going to use. This is now the shortest kind of laser pulse that you could make is out of this type of laser, because this is the titanium doped sapphire crystal. So that's like a ruby. A ruby is chromium doped, and that makes it redder, but Thai sapphire is sort of red. And so we pump it with a green laser. And then we just, it's not a standard cavity. A standard laser cavity would just have 2 mirrors. So this one has 2 curved mirrors here. What is an X-shaped? So we've come to 1 mirror here. So it isn't the cavity. Come from here, here, here. It would come back through there. And then actually, because this is folded, it goes to this mirror. And then it could go to this mirror. And that would need a cavity. And so when people first started to try to make short pulses, when they weren't too short, we didn't have to worry about dispersion. But once we got so many colors, and all colors travel through different optics, different speeds, that you would try to make the pulse short. By the time it went through all the stuff, it would be back long. Each pass, you would try to make it short, it would get itself long, make it short, get it long. And so that's where we have to put prisms in, and so that makes it back being short, and so after one round trip, it matches the pulse duration again. So that's the trick, is that we have to get all of that in there. But this is a short pulse. It makes 100 femtosecond pulses when it's turned on. And then the experiment, although the experiment isn't set up yet, but we're going to show it down there, is that we can take the light from here is so powerful that we will turn the infrared beam into blue.
Change the color of light.
We'll change the color of light.
Wow.
Yes.
So maybe you can explain how that works here. Change the color. Yeah.
So, this is how we're going to measure how short is this light. So the light comes in, and gets split into 2. One beam goes this way, one beam goes this way, comes here, comes back and goes out, comes in, comes out, comes out. So we'll have 2 beams on top of each other, and they'll change their timing, because when this glass plate's like this, there'll be equal timing. When it's like this one will be a shorter path. When it's like this will be the shorter path. And we turn it on, and that changes the path length between the two arms. And so we'll have two pulses walking past each other. And when they're together, we'll find a beam there that shows that you take one photon from this one photon from this one, going in different directions. It'll make a blue beam going in between them. We haven't got that set up yet. Can't show you that, but that's what we're aiming to do with this experiment. And so this is called an autocorrelator because it's taking its own pulse and going to measure the two. But if the laser turns on, we will show you the frequency though.
And this lab is actually meant for undergraduate.
Undergraduate lab, yes. And so they're going to get to play with this in the third year, but it's finally done. And in the second year, we'll just look at the frequency. In the first year, we're just going to look at the frequency doublet. It's ready. All righty. Hi. Oh, there it is. Named you. Okay. I prefer the old days when we just used to have a control box to go with the laser. It made more sense. All right, so now I got to get the laser to mode lock. Let's see if I can do it now. You want to just get the laser mode locking. Okay, so it has to start from noise. Oh, there you go. It's looking so well these days. Let me just... I don't know why it's way up high. I also knew how to work this laser. There we go. So those are the pulses.
Those are laser pulses.
Those are laser pulses, and so they come in every round trip of the cavity. So the beam makes one round trip, and every time it hits this mirror, 2% of the light goes this way, and then the rest go back around, get the gain, come back out again. So the round trip is about 10 nanoseconds or 10 feet. Or 3 meters. Okay, so let's see if we can get some frequency doubling here.
So there is light going right now?
There is now light going, so we all have our goggles on.
Okay.
Whoops.
And that's infrared? All
Okay,
right.
there's something that's really not stable here I'm going to have to fix. Right. Because one of these is not working now. Okay. So this is an IR card, so you can see the beam. Well, the two beams to cross at the focal thing. So let's just make sure that they're running parallel. They're not running parallel. Okay, now they're not crossing, but we're just going to start a green light, hopefully. Hopefully. What did I get there over there? Where's that optical diffuser now? Okay, so this is the crystal that will actually take the two photons and hopefully, if we're lucky,
Get one photon.
get one blue photon. Oh, there it is there.
It's a nonlinear crystal. What crystal is that?
I'm going to go with barium, beta barium borate.
Okay.
BBO.
BBO, I see. Oh, I can see that.
Can you see it on your camera?
Now I can see it with my eye.
Yeah, but it should be brighter than that. Maybe it's because I have the lights on. Hang on, we'll turn these lights on and those ones off. But that's the idea. And the experiment's going to be, why do we have infrared light here, turn in a blue light there? We're supposed to see if they can figure out what the theoretical model would be to explain that.
Wow.
That's the point of the project.
Let me thank you on behalf of bigyan.org.in for taking your time to talk to us.
বিশ্বের বিভিন্ন প্রান্তে ছড়িয়ে থাকা বাঙালি বিজ্ঞানী ও বিজ্ঞান প্রেমী দ্বারা পরিচালিত মাতৃভাষায় বিজ্ঞান প্রসারের একটি অব্যবসায়িক প্রয়াস bigyan.org.in বিজ্ঞান যারা ভালোবাসে বা ভয় পায় তাদের জন্য। এই পর্বটি ভালো লেগে থাকলে লাইক ও শেয়ার করে সবার সঙ্গে ভাগ করে নিন, আর আমাদের চ্যানেলটি সাবস্ক্রাইব করে আমাদের সঙ্গে থাকুন। কমেন্ট করে জানান আপনাদের মূল্যবান মতামত।
পরের ভিডিও প্রকাশের নোটিফিকেশন পেতে হলে বেল আইকনটি প্রেস করতে ভুলবেন না। আমাদের পাশে থাকার জন্য